Hi, everyone. Let's think about the big picture. We said in the example, there's insufficient evidence against the claim of independence, meaning that if I claim, you know what, I didn't think there's much of a relationship between party and gender. I think these are independent. So knowledge of the party doesn't really tell me about gender and vice versa. Yes, there are more women than men, but I don't think that's reflected in the party splits like this. Nah, doesn't matter. There's insufficient evidence against my claim. Okay, so you can't really say I'm wrong. You don't have enough evidence to say I'm wrong. Okay, this table is close enough to this table. Now, just for kicks, what about a case of clear dependence? Okay, let's put in some numbers. Let's say that 500 men are for the gray party, none for the yellow. Okay, the yellow party is for making men do chores everywhere, like all the time. Okay, and then with the women, let's say that 1,000 women are for the yellow party and 0 women are for the gray party. So the yellow party is saying, yeah, make men do all the chores. All right. Well, looky here. Here's the O table. Here's the E table. The two tables, how different are they? That's a measure. Wow, 1,500. That's your test chi-square. The 1,500, that's way out there, way, way out there. What's the right tail p-value? Close to 0. Basically 0. All right, this is a case where it definitely matters. Oh yeah, if you're a gray party, I think you're a man. Okay, if you're a man, I think you're a gray party. Okay. Also, remember the coins extra credit. Okay, the discrimination rule. I said that I thought the people who had a run of 5 or more heads or tails, I think you actually flipped the coins and the others faked it. That was the basic idea. Well, here are the results. Okay, one variable, I said you did it versus faked it. You actually did it versus faked it. Here are the results. Okay, notice I'm getting pretty strong numbers along that diagonal there. So I was making a lot of good calls. Here's the O table. Here's the corresponding E table. Test chi-square, about 8. That's out there. Okay. If you look at this distribution, the 8, that's pretty out there. All right. It's still pretty out there. P-value, right tail P-value, about 1/2 of 1%. Way less than alpha. So we reject the null of independence, which says that there is no relationship, which means, hey, this statistical test shows I'm a genius. It means that I'm definitely beating chance. Okay. For example, I'm doing much, much better than if I were to just flip coins myself and say, okay, I'm going to flip a coin. If I get a head, I said you did it for real. If I get a tail, I said you faked it. According to this test, I'm really, really beating chance. Okay, I'm really beating chance. Okay, so it looks like this rule is doing a pretty good job. All right. Key principle. Dependence does not imply causality. Statistical dependence does not imply causality. That is, just because we find that 2 variables are statistically dependent does not mean that there's a cause and effect relationship between the 2 variables. Not necessarily. Okay, so for example, look at this 2-way contingency table. Pet ownership, do you own a pet or not? And how'd you score on a test? Did you score above average on a test or below average? Okay. Well, it looks like here that the pet owners, there seems to be a relationship here where the pet owners seem to be doing better, and the people who do better tend to own pets. Now, does this suggest, for example, that owning a pet makes you smarter? I don't know. Maybe there is a psychology study that says that being around a pet makes your IQ go up. I don't know. I don't know if there's a study out there. I don't think that's the case. Okay. I think there might be a confounding variable. Maybe wealth or income, right? Maybe higher income families are more likely to own pets, right? And higher income families are also more likely to afford computers, additional resources, tutors, books, and so forth. So you might have a compounding variable like wealth. Sorry, not compounding, it's confounding. A confounding variable. like wealth. Okay. A confounding variable is a factor that we are not considering that is affecting both variables in the study. Here, a confounding variable could be income level, which could have a causal relationship with respect to both pet ownership and higher test scores. So income could affect both of these, okay? But maybe it's not so much going this way or that way. All right. And by the way, how are the E values calculated? Okay, well, basically, if you look here, the marginals are the same, right? The marginals are the same in both the tables. Basically, the idea is it's going to be row total times column total over grand total. So if you look at the O table, right, it's row, like for the first cell, the upper left cell here. How do you get the E value for the upper left cell there? It's the row total times the column total corresponding to that cell times the grand total. And it comes from independence. For example, the probability of men and gray, all right? Under independence, that's the probability of men times the probability of gray, right? Under independence, these probabilities split up. Okay, so the expected frequency will be n times the probability of men and gray, which is n times this product under the assumption of independence. If you work out the fractions, you get that formula. Okay, the formula being row total times column total over n for each cell. And then you have this variance looking thing, right? The square deviations are rescaling, some of those. Chi-square distribution on this number of degrees of freedom. And these were the numbers that led to the Excel result. Okay, well, up here. $1.2963. Again, for a 2x2 contingency table, it's similar to a test for proportions for independent populations. Okay, next up, more topics.